If I apply the inverse Laplace transform for this expression, it will become I of t, that is equal to, it is b by r, and for 1 by s it is 1, and it is 1 by s plus a. The inverse Laplace transform for this one is e power minus r by l into t. So this is the expression for the current that is flowing through the inductor RL circuit, through the inductor or through this RL circuit loop. So this expression for t greater than 0. If you want to find the voltage across the inductor, that is V of t or VL of t, that is L into dI of t by dt. So use this equation and differentiate this equation, multiply with L, then you will get the value of this VL of t. So this is how we can analyze this RL circuit using the Laplace transform. Now let me solve one problem on this RL circuit. There is a question here. That question, see, this is the network. This is voltage source. This is one position. It is second position, position 2 and position 1. Here it is 1 ohm resistor is connected like this. This is a switch, and this is the resistance 1 ohm. The inductor, it is 1 Henry. It is 1 ohm, and this voltage source value is 10 volts here. And the switch is moved from position 1 to position 2 at t is equal to 0. At t is equal to 0. Now I need to find the value of the current that is flowing through this loop, that is I of t. So determine I of t for t greater than 0 if the switch is moved from position 1 to position 2 at t is equal to 0. So I need to find this I of t expression for t greater than 0 if the switch is moved from position 1 to position 2 at t is equal to 0. So what I have to do here is how to solve this type of questions. If you want to apply the Laplace transform, or if you want to use the frequency domain analysis to solve this type of problems, then first thing what we need to do here is at t is equal to 0, what is the current that is flowing through the inductor, or what is the voltage across the capacitor. These two things we need to find. There is no capacitance here, so only the inductance. So I need to find the current flowing through the inductor at t is equal to 0 minus. T is equal to 0 minus is just before the switching action is done. At t is equal to 0, switching action is done. T is equal to 0 minus just before. T is equal to 0 plus just after the switching action is done. So just before the switching action, that means at t is equal to 0 minus, the switch is at position 1. So draw this network. So it is 10 volts. This is 10 volts, and this is the position 1, and this is position 2. It is 1 ohm, and this switch is connected to position 1. So this is resistance 1 ohm. So whenever the switch is at position 1, the circuit is under steady state condition. That means from minus infinity to 0, the switch is at position 1. So whenever the switch is at position 1, the circuit is under steady state condition. That means at t is equal to 0 minus, the circuit is under steady state condition. Under steady state condition, the inductor will act as short circuit. Okay. Now this current, I need to find the current flowing through this inductor, that is I of 0 minus. So try to find the current flowing through this inductor. So it is 10 volts, it is 1 ohm. So I of 0 minus is equal to 10 divided by 1 ohm, that is equal to 10 amperes. And we know that whatever the current that is flowing through the inductor at t is equal to 0 minus, same current will flow through the inductor at t is equal to 0 plus, and same current will flow through at t is equal to 0 also. So it is also I of 0 minus, that is equal to 10 amperes. So finally I of 0 is equal to 10 amperes. Why I need to find this I of 0, we can understand now. Now for t greater than 0, draw the circuit. For t greater than 0 means after the switching action is done. The switch is at position 2 now after the switching action. Now draw the same circuit here it is. So apply we need to draw the frequency domain circuit representation. In frequency domain, if it is a constant, it will become 10 divided by S volts. Now this is position 1, this is position 2. If there is a resistor, the same resistor we need to indicate. So this value is 1 ohm, and the switch is at position 2, and this is the resistance 1 ohm. Wherever the inductor is there, I need to replace this inductor with this inductance, that is Ls. It is minus and plus, it is L into I of 0. So to know the value of this I of 0, I am using this circuit at t is equal to 0 minus to calculate this 10 amperes, to calculate this I of 0. So L value here is 1 Henry. So 1 into S, that is S. L value here is 1 Henry. 1 into I of 0 is 10, that is equal to 10 volts. 10 volts. Now this is the current I of S now, I of S. Now write the KVL equation for this loop here. So it is plus and minus, it is plus and minus, it is minus and plus. Now minus of minus 2 into I of S minus Ls into, Ls means S, L value is 1 here, S into I of S here plus L into I of 0, that is 10, is equal to 0. Now S into I of S is equal to 10 minus 2, sorry, I can take it, so this is equal to this same expression. I can write this expression as 10 equal to 2, sorry, I of S, if I take I of S common in these 2 plus S. Just I bring this term to the right side, so this equation will become like this. So I of S is equal to 10 divided by S plus 2. Now I need to find the I of t. Take the inverse Laplace transform for this current expression I of S. So inverse Laplace transform for 1 by S plus A, that is equal to e power minus 2t. So this is the expression for the current flowing through this loop for t greater than 0. For t greater than 0. Now another thing here is analysis of RC circuit now. Analysis of RC circuit using frequency domain or Laplace transforms. Laplace transforms. Same expression, sorry. Draw the circuit. This is the resistance and this is the capacitance, RC series circuit. For this RC series circuit, we are applying the voltage, it is V here. So this is the value of our capacitance. At t is equal to 0, the switch is on. So the current will flow through this I of t. So I need to find this I of t, or I need to find the voltage across this Vc of t. Anything we can find. So to find this I of t at this Vc of t using this Laplace transform approach, I need to draw this same network for t greater than 0 using this Laplace transforms. So before going to draw this same network using the Laplace transforms, first what we need to do here is at t is equal to 0 minus, the switch is under open position, so no current will flow, no charge will be present across this capacitor, so no voltage will be stored across the capacitor. So the voltage across this capacitor V of 0 minus is equal to 0 volts at t is equal to 0 minus, that is equal to V of 0 plus, because the capacitor doesn't allow the sudden changes in voltage. So V of 0 is equal to 0 volts only. Okay. So now we draw this circuit for t greater than 0 now. For t greater than 0, the circuit, the switch was closed now. The switch will be closes like this. So this is the resistance. Since it is V constant, it will become V by S. Here the capacitance, I can replace the capacitance, and I can represent this capacitance in a frequency domain like this, 1 by Cs. If there is a voltage source, this voltage source will be like this, and this value of voltage source is V of 0 by S here. So V of 0 value is 0 volts anyway, I need not to represent this voltage source, so it will act as a short circuit now. So the same circuit can be represented like this, and this is the current I of S. It is 1 by Cs. It is I of S. This is V by S. It is R. Now let us apply the KVL for this, plus and minus, it is plus and minus. If I apply the KVL for this, V by S is equal to the voltage across this one, I of S into R, the voltage across this one, plus I of S into 1 by Cs. Now V by S is equal to, if I take I of S as a common, I of S into R plus 1 by Cs, that is equal to I of S into, it is RCS plus 1 divided by Cs, that is equal to V by S. This S and this S will get cancelled here. Now I of S from this equal to V divided by RCS plus 1. Now take RC as a common here, so V divided by RC into S plus 1 by RC. This is I of S. Now if I apply the inverse Laplace transform for it, L inverse of I of S is equal to I of t. If I apply the inverse Laplace transform, it will become V by RC e power minus 1 by RC into t. So this is the expression for I of t, the current flowing through the RC circuit. If you want to find the voltage across this capacitor, Vc of t is equal to 1 by C into integral minus infinity to t I of t dt. So now it is 1 by C into integral minus infinity to 0 I of t dt plus 1 by C into integral 0 to t I of t dt. So this is 0 anyway. Why? Because it is initial voltage. So this is initial voltage, that is V of 0 plus 1 by C into integral 0 to t I of t. You substitute this expression, that is V by RC into e power minus 1 by RC into t. Here I think I did a mistake here. So I forgot this capacitor C value here. S and S will get cancelled here. So I of S is equal to this VC, V into C. So I forgot to write this, V into C, V into C. So this C and this C will get cancelled here. So finally it will become V by R into this one. So this I of t expression here is, it is V by R into this one, it is T, V by R into e power minus. So it is V by R, I of t expression is, it is V by R into, it is e power minus 1 by RC into T. So V of 0 is, anyway it is 0. So it is constant, I can take it out from this integration, V by RC. If I integrate it, e power minus 1 by RC into T divided by minus 1 by RC. And this units 0 to limits 0 to T. So if I substitute these limits here, so Vc of t is equal to, or V of t, the voltage across the capacitor, V by RC into, it is minus RC. If I bring this denominator to the numerator, it will become minus RC into, if I substitute this t here, it is e power minus 1 by RC into T minus 0. If I substitute e power 0 is equal to 1. So it is this one. So this RC will get cancelled. So it is V into 1 minus e power minus 1 by RC into T. So this is the expression for the voltage across the capacitance. So we can find the expression for I of t for a RC circuit, and the voltage across the capacitance Vc of t for the RC circuit using the Laplace transform approach. Now let us solve one problem on this RC circuit using the Laplace transforms. Let us consider a problem here, a circuit. It is 10 volts. This value of this voltage source is 10 volts, and this is 1 ohm. This switch is A and this is B here. It is 1 ohm. This is capacitance 6 farad. This is the switch which is moved from position A to position B. The arrow mark indicates the switch is moved or shifted from position A to position B at t is equal to 0. Now this is capacitance, another capacitance, this whose value is 3 farad, and the voltage across this capacitance is, it is Vc of t, and the current flowing through this is indicated I of t. Here what I need to find here is I need to find or determine I of t and Vc of t if here for t greater than 0, if the switch is moved from position A to B at t is equal to 0. So I need to find these two things here, I of t and Vc of t for t greater than 0. So to solve this problem, first thing, at t is equal to 0 minus, how will be the circuit? At t is equal to 0 minus, draw the circuit and find the voltage across the capacitance. So at t is equal to 0 minus, the switch is at position A. This capacitance under steady state condition, it will act as open circuit. That means from minus infinity to 0, the circuit is under steady state condition. Under steady state condition, the capacitors will act as open circuits, and if there is any inductor, that will act as short circuit. So this is this capacitor will act as open circuit at t is equal to 0 minus. It is 1 ohm, it is 10 volts, 1 ohm, and it is 3 farad actually, it is 3 farad, it is 6 farad, and it is V6. I am assuming the voltage across the capacitor is V6 at t is equal to 0 minus, V6 of 0 minus. The voltage across the capacitor of 3 farad, that is V3 of 0 minus, and this is the voltage Vc of t, the voltage across this 3 farad. Now I am finding the voltage across the capacitor 6 farad, Vc of 0 minus. V6 of 0 minus is equal to, so this is one circuit, it is open circuited. So whatever the voltage that is present across this, same voltage will be present across this one, because if you apply the KVL, this voltage is equal to this voltage plus this voltage. Since no current is flowing through this resistance, the voltage drop across this resistance is 0. So this voltage is equal to this voltage. So this voltage is V6 of 0 minus is equal to this 10 volts. And we know that at t is equal to 0 plus, the capacitor doesn't allow the sudden changes in current. It is V6 of 0 plus is equal to V6 of 0 minus, that is equal to 10 volts. And we know that V6 of 0 is same 10 volts. So it is initial voltage, we found it. Next V3 of 0 minus. No supply is connected for this circuit, so no current is flowing. So what happens here is, it is 0 volts. V3 of 0 plus is equal to V3 of 0 minus is equal to 0 volts. Now V3 of 0 is equal to 0 volts. So these are the initial voltages across the capacitors. Now draw the circuit for t greater than 0. For t greater than 0. Now for t greater than 0, this circuit I can draw it as, it is 10 divided by S, Laplace transform circuit or frequency domain analysis I am using here. It is 1 ohm. Since the switch is moved from position A to position B, it is position A and it is position B, position A to position B. Now this is position A and this is position B, it is position B. This is the resistance 1 ohm, and here this is 1 by Cs, that is 1 by C value is 3 here. The voltage across this one, what is the voltage across this one is V3 of 0 divided by S, and here this capacitance, it is 1 by 6S, and the voltage across the capacitance, that is V6 of 0 by S here. Now this is the representation of the capacitors for t greater than 0 in S domain. V6 of 0, just now we calculated it as 10 divided by S. It is 0 divided by S, that is equal to 0. This circuit, this same circuit, and this current flowing through this current is flowing through this is I of S. Now the same circuit I can redraw, or otherwise apply the KVL directly. Why we need to redraw this? So it is plus and minus, plus and minus, plus and minus, plus and minus. So no voltage here, so it is 0. We need not to consider this voltage source. So here it is 10 divided by S, 10 divided by S, it is plus, current limited more. So I of S into 1 by 6S, it is minus I of S into 1, this one. Here this one is minus I of S into 1 by 3S. This voltage is anyway, it is 0, that is equal to 0. So if I take this I of S as a common and bring these all terms to the right side of the equation, it is 10 by S is equal to I of S into 1. It is 1 plus 1 by 6S plus 1 by 3S. Now it is I of S into, so here 6S, take this 6S as LCM here, so it is 6S plus 1 plus it is 2, right? 2 by 6s is 1 by 3s. We got it. So this one I of s into, it is 10 by s. This s and this s will get cancelled here. So it is 10, it is 6s. So if I multiply with this one, it is 60. 6 into 10, that is 60. 6s plus 3. So from this, I of s is equal to 60 divided by 6s plus 3. If I take 6 as common here, 60 divided by 6 into s plus 3 by 6, that is 1 by 2, that is 0.5. So it is 10. So it is 10 divided by s plus 0.5. So it is I of s. Here I need to find I of t. If I take the inverse Laplace transform for it, it will become 10 into e power minus 0.5 t. So this is the current expression for t greater than 0. For t greater than 0. Next, what I need to find here is Vc of t. So I of t is over. Next, Vc of t. So to find this Vc of t, the voltage across this capacitance Vc of t, this Vc of t is equal to 1 by Cs into this I of s, the current, the product of current into the impedance offered by this capacitance, that is 1 by 3s. Or I can also write this V of t, V3 of t or Vc of t. Normally in the problem he represents this one as Vc of t. Vc of t is equal to, Vc of s is equal to I of s into 1 by 3s. So this capacitance is 1 by 3s value. Anyway, this voltage is 0. Now this I of s, just now we calculated, we found this I of s as 10 divided by s plus 0.5. So it is 10 divided by s plus 0.5 into 1 by 3s. So it is 10 divided by 3 into 1 divided by s into s plus 0.5. Whenever this type of expressions are there, then I need to apply the partial fractions here. To find the partial fractions, just I am dividing with 0.5 and multiplying with 0.5, s into s plus 0.5. Why I am dividing and why I am multiplying, you can understand. 1 by 0.5 is 2. So 2 into 10 is 20 by 3. So 20 by 3 into s plus 0.5 minus s divided by s into s plus 0.5. So this s and this s will get cancelled, same 0.5 divided by this one. So 20 by 3 into s plus 0.5, s plus 0.5 cancelled. This s will get cancelled. So it is 1 by s plus 0.5. So now it is 20 by 3 into, it is Vc of s. If you apply the inverse Laplace transform for it, it will become Vc of t is equal to 10 by 3 into 1 minus e power minus 0.5 t. So this is the expression for Vc of t. This is how we have to solve the problems using the Laplace transform approach for a RC circuit also. Next, coming to this analysis of RLC circuit now. Analysis of RLC circuit using Laplace transforms. So draw the RLC circuit. This RLC circuit whose supply is controlled by this switch. Apply the supply voltage source V, it is R, L, C, and the switch is closed at t is equal to 0, so that the current will circulate through this loop is I of t. So what I need to find in this RLC circuit analysis using Laplace transform series, I need to find I of t. So this I of t, I'm going to find this I of t here. At t is equal to 0 minus, t is equal to 0 minus, the current flowing through the inductor is 0. The voltage across the capacitor is 0 because the switch is under open position. No supply is connected to this RLC circuit. So the current flowing through this inductor is 0. That is equal to I of 0 plus that is equal to I of 0 is equal to 0 amperes. And the voltage across the capacitance VC of 0 is also 0 volts. Vc of 0 minus is equal to Vc of 0 plus is equal to 0 volts, that is equal to Vc of 0 is equal to 0 volts. Now for t greater than 0, draw the circuit. If I draw the circuit, the switch was closed now. This same resistance is R. So this inductance can be represented with the Ls and this capacitance 1 by Cs. There will not be any voltages in series with Ls because L into I of 0, voltage source value is I of 0 is 0. So it is short circuited. See here it is, the voltage source value is V of 0 by S. So V of 0 is 0. 0 by S is 0. So there is no voltage source here also. So now this voltage source will act as V by S and this current is I of S. Now write down the KVL equation for this. It is V by S is equal to I of S into R plus Ls plus 1 by Cs. I of S into R is this voltage, I of S into Ls is this voltage, I of S into 1 by Cs is this voltage. So this voltage is equal to this voltage plus this voltage plus this voltage. So I wrote this KVL expression here. Now this is equal to I of S into, if I take this CS as a LCM RCS plus LCS square plus 1 divided by Cs. It is V by S. This S and this S will get cancelled here. So it is I of S into LCS square plus RCS plus 1 divided by C. I of S into LC, take a common here, S square plus R divided by L into S plus 1 by LC. This C and this C will get cancelled. So it is V. So now I of S is equal to, if I bring this term to the left side of the equation, it will become V by L into 1 by S square plus R by L to S plus 1 by LC. So it is a second order equation. So it will have some roots here. So S square plus R by L into S plus 1 by LC. If I make this equal to 0, it will have some roots for this equation. So let us assume those roots. So we already discussed this concept. S is equal to minus b plus or minus square root of b square R by L whole square minus 4ac. 4a value is 1 into c is 1 by LC divided by 2a. A value is 1 here. So if I write this, S is equal to minus R by 2L, I can write as, all this concept I already explained in previous classes, R by 2L whole square minus 1 by LC. If I bring this 2 into the square root, it will become like this. So it will have two roots here, S1 and S2. S1 is, let us assume, minus R by 2L plus square root of R by 2L whole square minus 1 by LC. S2 is minus R by 2L minus square root of R by 2L whole square minus 1 by LC. Now let us assume R by 2L is alpha. So it is minus alpha plus, it is square root of alpha square. Let us assume it is beta, it is omega naught. Omega naught square it is. So it is omega naught square. And it is minus alpha minus square root of alpha square minus omega naught square. where alpha is equal to r by 2l and omega naught is equal to 1 by root LC. And this total 1, let us assume it is beta minus alpha plus beta, it is minus alpha minus beta. Two roots S1 and S2 are minus alpha plus beta minus alpha minus beta for this expression. Now let us write this I of s is equal to I of s is equal to v by L into what is that 1 by s square, it is 1 by s square plus r by L into s plus 1 by LC. So it is having the two roots, that is S1 and S2. S1 is equal to minus alpha plus beta, minus alpha minus beta is this one. So it is v by L into 1 by s minus s1 into s minus s2. I can write like this. So it is having the two roots s minus s1, so it is s1 and s2. I can write this expression like this. Okay, where s1 is minus alpha plus beta, s2 is minus alpha minus beta. So this one I am writing this expression as like this: 1 by s2 minus s1, s2 minus s1 divided by s minus s1 into s minus s2. This s2 minus s1, s2 minus s1 will get cancelled here. So v by L into s2 minus s1, it is, I can write it as s minus s1 minus s minus s2. So this minus plus, so it is my s and s will get cancelled. So it is s2 minus s1, it will be s2 minus s1, s minus s1 into s minus s2. So it is v by L into s2 minus s1. So it is 1 by s minus s2 minus 1 by s minus s1. So if I cancel this term, it will become 1 by s minus s1. So it is I of s. So this expression, if I multiply with this, so it will become v by L into, so let us assume it is k1, that is v by L into s2 minus s1 into 1 by s minus s2 plus minus v by L into s2 minus s1 into 1 by s minus s1. So it is I of s, this is I of s, that is equal to this one, let us assume it is a constant, s2 is the roots here, so these are the constant, this is a constant, this is also constant. So let us assume this constant is k1 into 1 by s minus s2, and let us assume this is also a constant, k2 into 1 by s minus s1. So it is I of s. Now take the inverse Laplace transform for this I of s. L inverse of I of s is equal to I of t, that is equal to, so it is like 1 by s minus a. So the inverse Laplace transform is e power s2t plus k2 into e power s1t. So this is the I of t expression for RLC circuit, and it is having three cases here depending upon the values of r by 2l and 1 by root LC. It is having the three cases. Case number 1, if r by 2l is greater than 1 by root LC. What are the roots here? s1 is equal to minus alpha plus beta, or that is equal to minus r by 2l plus square root of r by 2l whole square minus 1 by LC. s2 is equal to minus alpha minus beta minus r by 2l minus square root of r by 2l whole square minus 1 by LC. Here omega naught is 1 by root LC, we know that. So it is alpha square minus beta square. Now if r by 2l whole square, if r by 2l is greater than 1 by root LC, that means this term is positive. So it is positive. So the square root is also, suppose it is so it is positive. So it is totally positive. So it is having the two roots which are minus alpha plus beta and minus alpha minus beta. These are the real roots, real and different roots. The roots are real and different roots. I already explained, if the roots, it is an S-plane here, it is an S-plane, it is real axis, negative real axis, imaginary axis, negative imaginary axis. If the poles are placed, the poles are located on the imaginary axis, then the system is undamped system. If the poles are located in between, the poles will come like this pole will come like this pole and this pole will collide like this. One pole is moving in this direction, here it is one pole will move like this, here it is another pole like this. Let us assume like that. So this pole is coming like this, this pole is coming like this. So in this case the system response is undamped system or undamped response. If the roots are located in this place, then that is underdamped system. If the two roots are here, then that is critically damped system. If there are this root and this root are present in negative real axis, which are different here, then that is overdamped system. So here this is one root minus alpha plus beta. It is one root minus alpha minus beta. This is this root. So these two roots are on negative real axis and these two roots are different roots. So the system response here is, here the system response. The system response is overdamped system, and that response is I of t is equal to, same thing it is, roots are different here, e power minus alpha t, sorry, e power minus alpha plus beta into t plus k2 into e power minus alpha minus beta into t. So that is equal to, if I take e power minus alpha t common, e power minus alpha t, k1 into e power beta t plus k2 into e power minus beta t. So this is the expression for I of t for this case. Now case number 2. In the case number 2, if r by 2l is equal to 1 by root LC, then what happens? R by 2l is equal to 1 by LC, whereas r by 2l whole square is equal to 1 by LC. Then this term will become 0. That means this beta is 0. So S1 is equal to minus r by 2l, S2 is equal to minus r by 2l, that is equal to minus alpha. So the two roots are same. So then S1 is equal to minus alpha, that is equal to minus r by 2l. S2 is equal to minus alpha, that is equal to minus r by 2l. So the two roots are same. The two roots are same and real and same. That means it is a negative real axis. So two roots are same. One root is present here, another root is also present here. So the system response is critically damped system. And the system response is critically damped system. And the expression for I of t, if the two roots are same, then the expression for this I of t we already discussed here according to the differential equations. I can write as e power minus alpha t into k1 plus k2t. This is the expression. Now case number 3. If r by 2l is less than 1 by root LC. That means if r by 2l is less than 1 by root LC means the value in the square root will be negative. So I will take this negative sign out of this root by introducing the complex number. So now S1 is equal to minus r by 2l plus square root of r by 2l whole square minus 1 by LC, and S2 is equal to minus r by 2l minus square root of r by 2l whole square minus 1 by LC. We know that it is minus alpha plus square root of alpha square minus omega naught square. This is minus alpha minus square root of alpha square minus omega naught square. So here if I take the negative sign here, it is minus alpha plus j, that is square root of minus 1 is j or I into square root of omega naught square minus alpha square. I can write like this. This is also minus alpha plus j into square root of omega naught square minus alpha square. It is minus alpha plus j into, this value is omega d. Here also plus j into, it is omega d, where omega d is equal to square root of omega naught square minus alpha square. So two roots now. The new two roots are, it is minus alpha plus j omega d, and S2 is minus alpha minus j omega d. So if I write the expression for I of t, two roots are here, k1 into e power minus alpha plus j omega d into t plus k2 into e power minus alpha minus j omega d into t. So e power minus alpha t, k1 into it is e power minus alpha t, I can write this expression as e power j omega dt. k2 into it is e power minus alpha t into e power minus j omega dt. Take this e power minus alpha t as a common here. It is k1 into e power j omega dt plus k2 into e power minus j omega dt. So it is e power minus alpha t, k1 into this one as e power j theta, that is cos theta plus j sin theta. So that is cos omega dt plus j sin omega dt plus k2 into cos theta minus j sin theta it is. So cos omega dt minus j sin omega dt. So it is e power minus alpha t into, so cos omega dt, cos omega dt. Take cos omega dt as common here, k1 plus k2 plus j sin omega dt. Take common here sin omega dt. it is k1 minus k2. So this is the expression for I of t for the third case. Here see, if you consider these two roots, s1 is equal to minus alpha plus j omega dt plus j omega d minus alpha minus j omega d. So these are complex conjugate roots, that is it is minus alpha, that is a negative real axis, minus alpha plus j omega d. This root will be like this, minus alpha plus minus j omega d. This root will be here, minus alpha plus j omega d. So minus alpha, this value is minus alpha plus j omega d minus alpha minus j omega d. So if the two roots are in this place or in this space, then this is comes under damper system. So since the two roots are complex conjugate roots, the system response is underdamped. Okay, so this is the analysis of RLC circuit using the Laplace transforms. Now coming to this, let me solve some of the problems on this RLC circuit so that I will conclude this session. So draw this network here. So there is a voltage source, it is 5 volts, and this is a switch. This value is 2.5 ohms, and this is 200 microfarad, and this is inductance, it is 0.5 Henry. So this is the problem, and the switch is opened at t is equal to 0. What I need to find here is this, determine the current through the inductor. So determine the current through the inductor. So I need to find the current through the inductor using the Laplace transform approach. This is the circuit. For this circuit, at t is equal to 0, the switch is open. That means at t is equal to 0 minus, the switch is connected here. I need to find the current through the inductor for t greater than 0. So any problem, the first step that we need to do here is finding the current through the inductor at t is equal to 0 minus and voltage across the capacitor at t is equal to 0 minus. So draw the circuit at t is equal to 0 minus. So t is equal to 0 minus, the switch is connected. So it is 5 volts. This switch is connected here. It is 2.5 ohms. Under steady state condition, from minus infinity to 0, this circuit is under steady state condition because the switch is connected for a long time. So under steady state condition, the capacitor will act as open circuit and this inductor will act as short circuit. So this is voltage VC or VC of 0 minus and the current, that is IL of 0 minus. So this voltage VC of 0 minus is equal, this voltage is equal to this voltage because these two are connected in parallel. So this voltage is 0, short circuit voltage is 0. So VC of 0 minus is equal to 0, so that is equal to VC of 0 plus. So VC of 0 is equal to 0 volts. This is the initial voltage across the capacitor. Now the current through the inductor IL of 0 minus is equal to, so since the current is flowing in this direction, there is a path available, so that is 5 divided by 2.5, that is 2 amperes. So IL of 0 minus is 2 amperes, that is equal to IL of 0 plus, so IL of 0 is equal to 2 amperes. So we calculated this initial voltages and currents across the currents through the inductors. Now for t greater than 0, draw the circuit. The switch is opened, so there will not be any effect of this 5 volt source on the circuit because the switch is open, and this is 2.5 ohms. This capacitance I can replace with 1 by Cs, 1 by 200 into 10 power minus 6 S. So the value of the voltage is 0, so that is V of 0 by 0, V of 0 by S is equal to 0, so it will act as a short circuit. Okay, short circuit. And this inductance Ls, so it is L value is 0.5 into S, and this voltage source, this value is L into I of 0, so L value here is 0.5 into I of 0 is 2, that is 1 volt. So this value is 1 volt. Now this current is, let us assume this current, it is I of S. Okay, so apply the KVL here, it is plus and minus, it is minus and plus. So here it is, let us consider this one, I of S into 1 by Cs, that is 1 by 200 into 10 power minus 6 S. Since it is negative, current limit terminal is negative, so it is minus. Here current limit terminal is negative, so it is 0.5 S into I of S. And the current limit terminal here is positive, so plus into 1 volt, 1 is equal to 0. Now if I bring this term to the right side of that equation, 1 is equal to I of S, take as a common here, it is 1 by 200, so 1 by 2 into 10 power minus 4 plus 0.5 S, it is S here. Okay, it is I of S into it is 1 by 2, it is 0.5 into 10 power 4, it is 0.5 into 10 power 4 divided by S plus 0.5 S. So take 0.5 here, it is I of S into 0.5, so it is 10 power 4 plus S square divided by S, it is 1. So now I of S is equal to, from this, S divided by 0.5 into S square plus 10 square whole square. This 10 power 4 I am writing 10 square whole square. Now if I apply the inverse Laplace transform for this L inverse of I of S, it is I of t is equal to, it is S divided by S square plus omega square, so it is 1 by 0.5, so it is cos omega value is 100 here, it is 100t, cos 100t, so it is 2 cos 100t. So this is the expression for current flowing through the inductor for t greater than 0.